Hi, I'm Mrs. Hilton, and for today's lesson, you're going to need a piece of paper and something to write with. In our previous lessons, we've looked at what functions are and some different ways to represent them. Today, we will look at and review those things and learn what linear equations are and how to compare linear and nonlinear functions. As we look at this first slide, we can see the title of the lesson is Graphing Linear Functions. We've talked about graphs and functions, so take a minute to think about what you think linear means and how it might apply to this lesson. There are two parts to today's I can statement. The first part states, I can recognize a linear equation is graphed as a straight line, and the second part says, I can compare linear and nonlinear functions in different representations. In this lesson, we'll do 4 different things. We'll begin by reviewing relations and functions. Second, we'll go over new vocabulary. Third, we'll identify linear functions. And fourth, we'll practice to show what we know. Let's review. First, a relation connects one set to another set where one, some, or all x values can have more than one y value. For example, we see these ordered pairs. We can see that 4 is the x input for 2 of the ordered pairs, which gives us 2 separate y outputs, which means that this cannot be a function. It is just a relation. We can see that also here in this map, that 4 and 9 both have 2 different outputs. A function is a specific type of relation that connects one set to another set, where each x value has only one y value. For example, in the ordered pairs here, we're comparing letters of the alphabet to their place in the alphabet. So we can see that A correlates with 1, B correlates with 2, and C correlates with 3. Functions can be represented many ways. Let's review some of the ways we saw them in our last lesson. Using the equation y equals 2x minus 3, we can choose 5 values to solve for y. You can pause the video here and practice, see if you can remember any of the ways we wrote these ordered pairs in the last lesson. If you wrote ordered pairs, your answers might look something like this. If we use -1 as our input or x value, we get y equals -2 plus -3, or y equals -5. So you can see in this first ordered pair, we have an x value of -1 and a y value of -5. If you chose to map this equation, it might look something like this. You could have used 0 for your x value. If we substitute 0 into our equation, we would get 0 minus 3 equals y, or -3 equals y. So we can see that in the second space here on the map, we have 0 for an x value and -3 for a y value. Continuing on, the table shows kind of the same thing. So you could check your work for 1 for x. If we substitute 1 into our equation for x, we get 2 minus 3, which means our y value would be -1. So these are all the same types of correlations. The last way we can show this equation is by using a graph. Here on this graph, we can see the x and y values are plotted as dots. So we can see that our first ordered pair here that is -1 and -5 is this first dot here down in the bottom. Then the second dot that's mapped on this graph or plotted on this graph is 0, -3. And then we have 1, -1, 2 and 1, and then 3 and 3, and then the lines drawn through. Okay. Graphs allow us to look at an entire set of data at a time. This lets us focus on a whole rather than a specific point. We can classify functions based on their graph much more quickly than we could by just looking at the equation alone. We will see this throughout the lesson today. Some of these words on our vocabulary list you might know already, and some might be new. A function is a specific type of relation that connects one set to another set where each x value has only one y value. The x and y value in a function can be called the input and the output, or the independent and dependent variable, or the domain and range, or simply the x and y value. Linear functions are functions whose graph is a straight line. They usually have constants and simple variables. The variables do not have exponents or square roots or cube roots. Nonlinear functions are not graphed as a straight line, meaning they are curved and can have exponents or square roots or cubed roots. Today we'll practice identifying linear functions as equations and in graphs. When we ask what are linear functions, the first rule is, to be a linear function, the change in y and the change in x must always be constant. Let's look at some examples. Here in this table, we see some x and y inputs and outputs. Go ahead and look down the x column here first and compare the variables. See if there's anything that you notice about them. You can pause the video if you need to. Did you notice that the change between each x value is 4? For example, if we take -7 and add 4, we end up with -3. If we take -3 and add 4, we end up with 1. And if we take 1 and add 4, we end up with 5. So the rate of change between our x variables is 4. Go ahead and look at the y column and see if you can determine what the rate of change is there. You can pause the video if you need to. Here we can see, as we compare these numbers, that 4 take away 1 equals 3. If we do 3 minus 1, we get 2. 2 minus 1 gives us 1. So the rate of change here is -1. When we write this rate of change as y over x, we can see it as -1/4 for each input and output. It's the same. Let's go ahead and look at another example. In the x column, see if you can determine what the rate of change is for this table. As we look at these values, we can see that 1 plus 1 will equal 2, 2 plus 1 will equal 3, and 3 plus 1 will equal 4. In the y column, see if you can determine what the rate of change is. In order to get from 11 to 14, we add 3, but to get from 14 to 19, we would have to add 5, and to get from 19 to 26, we would need to add 7. If we write our rate of change as x over y again, we would get 3 over 1, 5 over 1, and 7 over 1 for each of these ordered pairs. So in this table, our rate of change is not constant. Based off of what we have learned about linear functions, which is this rule right here in blue, to be a linear function, the change in y and the change in x must always be constant. Which of these examples would you say is a linear function and which is not? Example 1 is a linear function because it follows the rule that the rate of change is constant. Example 2 is not a linear function because the rate of change is not constant. Are tables the only way to check the rate of change to see if a function is linear? Let's try a word problem and see. First, let's look at something we know about linear equations. When the rate of change is constant, the graph is a straight line. As you might have predicted earlier when I asked you to think about what linear means line. So a linear equation is always going to be graphed as a straight line. We will see as we graph linear functions, the graph is always a straight line. Let's look at a word problem. Hannah will be charged an $8 fee to join the local swimming pool. Each time Hannah goes swimming, she'll be charged an additional $2. Using y as our total cost and x as the number of times Hannah visits the pool, we can write an equation. Y equals 2x plus 8. The next part of this word problem is going to ask us to graph the amount spent if Hannah goes to the pool 1 time, 5 times, and 10 times. So let's go ahead and do fill in the equation with this. We know that our X value is going to be the number of times she goes swimming. So let's go ahead and substitute 1 for X in our equation first, which is going to leave us with 2 times 1 plus 8, which is going to be 2 plus 8, which means our Y value is going to be $10. So our ordered pair here would be 1 and 10. Our X value was 1 and our Y value was 10. Let's go ahead and do this for the next one. If Hannah goes to the pool 5 times, we'd have 2 times 5 plus 8, which is going to give us 10 plus 8, or 18. So our Y value is going to be 18. When we write that as an ordered pair, we'll have 5 as our X value and 18 as our Y value. And for our last one here, let's substitute 10 in as our X value. So if Hannah goes to the pool 10 times, we have 10 times 2, which gives us 20, plus 8 is going to give us 28. So our ordered pair here is going to be 10 and 28 for our X and Y value. Now that we've figured out what these ordered pairs are, we can use these and plot these points on a graph. So what our function would look like as a graph is this. We can see that this function is a straight line, which makes it a linear function. Using this graph, we can also see that the different X and Y value for each variable without having to fill them into an equation. This makes checking our data easy. Now that we have seen the rule when the rate of change is constant, the graph is a straight line, let's try another equation. Let's try to think about if this equation is linear or nonlinear. The equation is y equals x squared minus 4. Let's go ahead and solve this with x equaling the following amounts. So if we substitute -3 in for x first, we would see -3 times -3, which is going to give us 9, minus 4, it's going to give us a y value of 5. So our ordered pair for this would be -3 for our x value and 5 for our y value. Next, we can substitute in 0 for x. So we'll have 0 times 0 minus 4, which is going to give us 0 minus 4, which means our y value is going to equal -4. So for our ordered pair, we'll have 0 and -4. And last, we're going to substitute 3 in for our x value, which will give us 3 times 3, which we know is going to be 9 again. Take away 4 will give us an x value again of 5. So our ordered pairs for this will be 3 and 5. Next, let's go ahead and plot these on a graph and draw a line connecting them. We can see that this line is curved, not straight, which makes this a nonlinear equation. Is there another way we can tell if the function is linear or nonlinear? Another way to tell if a function is linear or nonlinear is to look at how the equation is written. Most linear functions follow this pattern. Y equals mx plus b. In this equation, b is going to be the y-intercept and m is the slope. As we can see in this example here, let's talk a little bit about what we see. In this example, we see the equation y equals 2x plus 1. We can see here on the graph that where the blue line intersects the y-axis is right at the number 1. Okay, so that is called the y-intercept. The b in that equation is 1, and that's where that line crosses the y-axis. So we see it in the equation right here where the yellow circle is. Next, let's look at m, which is the slope. The slope in this equation is 2. If we look over here on the graph, we can see that after we intersect the line, the y-axis here at b, the 2 is going to take us up 2 and over 1. which is also referred to as rise over run, or the slope of the line. And it's going to continue the same way. That rate is going to be constant because this is going to be a linear equation. When we see an equation written in this form, we know that it is linear and that will be a straight line on a graph every time. So this is another way we can check to see if an equation is linear or not. What other ways can we see if a function is linear or nonlinear? Some examples of nonlinear equations might look like these. Y equals x squared plus 2, or y equals the square root of x plus 6. In this example, we see an exponent here in the first, that 2 is a square. Okay, we know that if there's an exponent, this equation cannot be linear. We saw that in the example earlier and in the rule in the vocabulary slide. We also have a square root in this next example. It asks for the square root of x, and we know that in a linear equation, it cannot have an exponent or a square root. So neither one of these equations can be a linear equation. They are both going to be nonlinear. Now that we know some ways we can tell if a function is linear or nonlinear, let's practice. If we're given the statement that Giselle runs 3 miles in 21 minutes, we can take the distance that Giselle can run and make it a function of the amount of time she spends running. We can write it as an equation in 2 variables that represents her distance run. We'll write that as y. And as a function of the time, we'll write the time as x that she spends running. So y will equal the distance and x will equal the time. We know that she can run for 3 miles. So that'll be the top. We're going to put y over x. So we'll have 3 on top. And then 21 is going to be the time that she spent running. That number will go on the bottom. Okay, so we know what we're going to need to isolate the y on one side of the equation. So in order to do that, we'll multiply both sides by x, which will give us this function here. We'll see x 3 over 21 equals y. That fraction can be simplified. 3 goes into 3 1 time, and 3 goes into 21 7 times. So what our equation is going to look like here at the end is going to be y equals 1/7 x. So what can we do with this? We have this equation y equals 1/7 x, where we know that y equals the distance and x equals the time. If we use this equation to determine how many miles Giselle can run in 14 minutes, we know that 14 minutes is a unit of time, so we can substitute that number in for x. So we'll have 1/7 of 14, or we can just divide 14 by 7, which will give us 2. So Giselle can run 2 miles in 14 minutes. We can then use the equation to determine how many miles Giselle can run in 28 minutes. Again, 28 minutes is the time, so that's our x value. We're going to substitute that into the equation there. We'll have 1/7 28, or 28 divided by 7, which is going to give us 4. So we know that in 28 minutes, Giselle can run 4 miles. In this last one, let's use the equation to determine how many miles Giselle can run in 7 minutes. So because we know 7 minutes is the unit of time, we'll substitute it for x. And then 7 divided by 7 gives us 1 mile. Giselle can run 1 mile in 7 minutes. Each of these answers gives us a set of an ordered pair. So we can see that in 14 minutes, that's our x value. She ran 2 miles, so 14 is our x value, 2 is our y value. And in the second equation, we have 28 minutes, which is going to be our x value, and then 4 miles will be our y value. And then our last one is going to be 7 minutes and 1 mile. So we can use these ordered pairs to graph. And we see that our graph looks like this. We can plot these points and draw a line. And based off of what we see here, do you think that our equation y equals 1/7 x is a linear equation? We can see that because the graph is a straight line, this is a linear equation. Is there another way we can tell if this is a linear equation? Can we look at the equation itself and determine from what we see there that this is a linear equation? You might have noticed that the equation y equals 1/7 x follows the slope-intercept form. So we can tell the equation also, we can tell just from the equation that this is also linear. Now that we've practiced identifying linear and nonlinear equations, let's see what you know. In this first example, what shape do you expect the graph of the function described by y equals x to take? Is it linear or nonlinear? You can pause the video here and take as much time as you need to think about this. If we graph y equals x, we can see that our x and y values will be identical if x equals y. So our graph would look like this. As you can see, the points that could be marked here on the graph could be at 1 and 1 or 2 and 2. So do you believe that this is a linear or non-linear function? We can see on the graph that it's a straight line. So based on the fact that the line is straight, we can guess that we can state that this is a linear equation. Let's go ahead and look at another example. In example 2, it says, what shape do you expect the graph of the function described by y equals 2x squared minus x to take? Is it a linear or nonlinear function? Because this equation has an exponent, we can assume the graph will have a curved line like this. This curved line indicates that this is a nonlinear function. Is there another way to tell this? If we look at the equation itself, we can tell that this is a nonlinear function because the equation has an exponent in it. And if an equation has an exponent, it cannot be a linear function. So there's two different ways we can tell there. Let's look at one more example. What shape do you expect the graph of the function described by y equals negative 2x plus 4 to take? Is it a linear or nonlinear function? Again, you can pause the video here to take as much time as you need to decide what you think. To begin with, we know that the y-intercept of this equation is 4. Okay, so if we look at this graph here, we can see that this line intersects the y-axis right at 4. Okay, we can see that the slope of this line is negative 2. It shows that that shows us that this line will go down two lines on the y-axis for each time it moves over 1 on the x-axis, and that rate is going to be constant. So this is a linear equation. The rate of change is constant. It's a straight line, and we can again tell from the equation that is written in slope-intercept form that this equation is a linear function. In this lesson, we talked about 3 different ways to determine if something is a linear function or not. One way to determine if a function is linear or nonlinear is to inspect the average rates of change using a table of values. If these average rates of change are not constant, the function is not linear. That was our first example. Another way to examine if a function is linear or not is to check the graph of the function. If all the points on the graph do not lie in a common line, then the function is not linear. If the line on the graph is not straight, it's not linear. This was our second example. In our third example from the very beginning, we saw that if a function is described by an equation different from one equivalent to y equals mx plus b for some fixed values of m and b, then the function is not linear. We call this the slope-intercept form. If your equation's written that way, it is linear. When you graph it, it will show up as a straight line. By graphing equations, we can look at an entire set of data at a time. This allows us to focus on the behavior of the function as a whole rather than just a specific point. We can classify functions based on their graph much more quickly than we could by just looking at the equation. Graphs of functions allow us to determine specific information such as an object's height as it falls. Thank you for working with me this week on functions. I hope that you were able to learn a few things and that you are able to use your notes to help you as you go throughout practicing these different skills.